All right, so in this video, we're going to take a look at some problems that involve cosine, sines, tangents, all of sums and differences. The first example we'll look at would be cosine of 7 pi over 12. Now, the first thing that hopefully you notice is that 7 pi over 12 does not give us one of our special triangles that we've been studying or anything that we know that comes straight from the unit circle. So what we're going to do is we're going to take that 7 pi over 12 and we're going to split that into a sum or difference of things that we know that give us 7 pi over 12. And what I mean by that is you can see that 7 pi over 12 is the same thing as pi over 3 plus pi over 4. Both of these, the pi over 3 and the pi over 4, separately, I know a lot about them. And so I'm going to view this as cosine of a sum, pi over 3 plus pi over 4. So the cosine of a sum identity would give us cosine of pi over 3, cosine of pi over 4, minus sine of pi over 3, sine of pi over 4. So now separately we can figure out what each of those are going to be, and I won't do this for all of the problems that you see throughout these next couple sections, but the first one I will go ahead and draw it out. Pi over 3, if we have our pi over 3 here, this would be a 1, a 2, a square root of 3, and our pi over 4 triangle would be a 1, 1, and a square root of 2. So for the first one, cosine of pi over 3. Cosine of pi over 3, if you look at your triangle, would give us 1/2. Cosine of pi over 4, if you look at the triangle, would give us 1 over root 2. Sine of pi over 3 would be a root 3 over 2. And the sine of pi over 4 would be a 1 over root 2. So combining these, we get 1 minus the square root of 3 over 2 square root of 2. We could certainly rationalize this if we needed to, but for now I'll just go ahead and leave that as the final answer, and that is what cosine of 7 pi over 12 is by breaking it apart into cosine of a sum. All right, so in the next example we've got cosine of alpha given, cosine of beta given, information about alpha and beta, but we're trying to figure out sine of alpha minus beta, so sine of a difference. So similar to the last one, I'll go ahead and write out the identity for sine of a difference, which would be sine of alpha cosine beta minus sine beta cosine alpha. And now it's just a matter of filling in some things we know and looking for finding the things that we're still missing. So sine of alpha is still a question mark. Cosine of beta we know. Sine of beta is still a question mark. And cosine of alpha we know. So I'll go ahead and drop in the things that we know. Still missing sine of alpha. Cosine beta is negative root 2 over 3. Sine of beta is missing, and cosine of alpha is a square root of 3 over 4. To find those missing individual pieces, now we'll come back over and we'll draw our triangles. Alpha is in quadrant 1. So since cosine of alpha is the square root of 3 over 4, to find the missing side there, we would use the Pythagorean Theorem. So we could see that square root of 3 squared plus y squared would equal 4 squared. So y squared would equal 16 minus 3. So y would equal the square root of 13. Similarly, with beta now, this is our beta, being in quadrant 2, cosine of beta is negative square root of 2 over 3. To find the missing side once again, we'll have to go ahead and use the Pythagorean Theorem. In doing so, we end up with the square root of 7. So sine of alpha would be the square root of 13 over 4. The sine of beta would be the square root of 7 over 3. And putting this all together now, you can see that we would get a negative square root of 26 minus the square root of 21 all over 12. And there's really not much simplifying that can be done here, so that would be our final answer for that one. So now we're ready to go ahead and prove an identity. Again, to pick a side, it's a little bit subjective, but whatever suits your eye the best, knowing that you're going to have to turn it into the other side. I personally would probably start with the right-hand side here. I would take the right-hand side and be sure to write it down. And then, seeing as we're in cotangents and we want sines and cosines, it would probably make the most sense to convert these to sines and cosines. So we'll have cosine of y over sine of y plus cosine of x over sine of x divided by cosine of y or sine of y minus cosine of x over sine of x. Now, to clear the complex fraction, I'll need to multiply top and bottom, what looks to be the LCD of everything, as sine of x, sine of y. Once again, top and bottom. And when I now take that and I distribute it to all of the parts, you can see that I would end up with, in that first term, a sine of x cosine y plus cosine x sine of y. And in the denominator, pretty similar, I would have cosine y sine of x minus cosine x sine of y. And if you look at both of those separately now, the top would be the sine of a sum, x plus y, and the bottom would be the sine of the difference, x minus y, which is the left-hand side. All right, in this example, there's quite a bit going on. So I would probably go ahead and start with the right-hand side, at least momentarily. My right-hand side, when I write it down, there's a couple of things that I'm looking at, and I know that I can do pretty quickly to make this hopefully look a little bit better. So again, just right now, I'm writing it down. And the few things that I see right off the bat are the sine of the t minus pi over 2 and the cosine of v minus pi over 2, both of which look pretty similar to cofunction identities. Now, remember, the cofunction identities would be the pi over 2 minus the angle, and this is backwards, which is okay. We just need to make the appropriate adjustments. So sine of t minus pi over 2, that's going to be the same thing as sine of negative pi over 2 minus t. So I factored a negative out, and now I have it in the correct order. Sine is odd, so the negative would have to come out. So really, what's given to us in the initial problem right here, that's the same thing as negative sine of pi over 2 minus t, which is also negative cosine of t. Now, I'm going to replace that in the next step, but I also want you guys to think about the cosine of v minus pi over 2. If I do the exact same thing with cosine, going from this step to this step, cosine's an even function, so the negative would get absorbed. So conveniently, cosine of v minus pi over 2 is the same as cosine of pi over 2 minus v. And then again, that's all because cosine's an even function. So I'll be able to replace this with just a sine of v and not having to take any other precautions. So let me go ahead and sketch that out. We've got our cosine v, and we've got our negative cosine t. Now we have a minus sine v and a sine t all over sine squared t minus cosine squared v. Okay, my next step is just going to be a little bit of cleaning up. I'm going to go ahead and factor a negative out of here, and I'm going to drop it into the denominator. And then this is just more so we don't make a silly mistake later on. So cosine v cosine t plus sine v sine t all over cosine squared v minus sine squared t. Now, you might be thinking, well, that numerator is an identity, and it's true, it is, but I don't know that I'm going to get too crazy with it yet, because I know that I'm trying to make it look like this. And to be fair, I don't really know what this even looks like. So I'm going to go ahead and actually change this out here and jump over to the left-hand side. So LHS secant of v plus t, I know is 1 over cosine of v plus t, which is 1 over cosine v cosine t minus sine v sine t. So it's almost like we have something backwards, if you will. We've got the cosine, we've got the plus on the top, and we've got the minus on the bottom. So we're in a position now where it actually makes sense to put what we want in the problem. And what I mean by that is I very clearly want this in the numerator, and I don't have that. So I'm going to go ahead and I'm going to multiply top and bottom of this by the cosine v cosine t plus sine v sine t. So let me go ahead and do that and see what happens here. So cosine v cosine t plus sine v sine t, and in the denominator it'll have to be the same thing. Now this might get a little crammed in here, so maybe I'll write it below. Cosine t plus sine v sine t. Now in the numerator it's the standard cosine v cosine t plus sine v sine t that I put there. And in the denominator now I'm going to take this and have to multiply it by that. Now conveniently those are going to be conjugates, so it's really not going to be as bad as it looks. And when I do this, I'll get a cosine squared v cosine squared t minus sine squared v sine squared t. Okay, so now I went ahead and multiplied that out. My numerator is good. I've got this and I've got that. All looks good in the numerator. In the denominator, though, I've got some things that I don't want. So look again at where you're going. We want cosines with v's and sines with t's. What we don't want would be cosines with t's and sines with v's. We don't want those there. So what we'll need to do is go ahead and rewrite them. And so I'll rewrite them using the Pythagorean identities. So give me a second here to copy all this stuff down. So I've got my cosine squared v, which is good, and 1 minus sine squared t, and then a 1 minus cosine squared v with our sine squared t. And then we'll distribute, and notice on the bottom the only things we'll have will be things that we want, cosines with v's and sines with t's. So when I distribute, I'll get a cosine squared v minus cosine squared v sine squared t minus sine squared t plus sine squared t cosine squared v. And conveniently, the part that we don't want in our final answer zeroes itself out. So final answer, final step in this proof would be to match up what we have in the previous line with what we're shooting for on the right-hand side, which is cosine squared v minus sine squared t in the denominator. So there's our RHS, and that takes care of that one.